All right, so the next section, we're going to be taking a look at different types of titrations, different types of acid-base titrations, to be more specific. And again, titration is just the technique of adding a base to an acid, for example, to react all of it away. And based on the volumes that are used and the concentrations, we can calculate the concentration of an unknown, whatever the unknown is in our system that we're studying. So there are three different combinations that we're going to see. We're going to be looking at strong acid versus strong base titrations. So SA for strong acid, SB for strong base. We're also going to be looking at weak acid versus strong base titrations. And then the last combination we'll see here is a strong acid versus a weak base titration. Okay, so there are three different types that we're going to be looking at. The first one is a strong acid, strong base titration. So for example, we have hydrochloric acid, HCl, and the strong base sodium hydroxide, right? We know that these will dissociate completely to give us H plus Cl minus. The sodium hydroxide gives us Na plus and OH minus. So we can write the equation, the overall equation for this, or we can just write the net ionic equation, which is really what's happening here. And what's really happening in the strong acid, strong base, the proton and the hydroxide combine to give us H2O, right? And that's the net ionic equation for any strong acid, strong base titration. Let's take a look at how we can chart this in a titration curve. For a strong acid, strong base titration. So we're starting off here with the pH of our strong acid, originally about 1. And then as we add sodium hydroxide, what we see is that the pH stays fairly constant initially. And then at some point, there's a very drastic change in the pH. So this section here, okay, drastic pH change. And right in the very center of that is our equivalence point, where all of the acid has been neutralized by the base. And then if we keep adding more base to it, right, we'll see that the pH changes, but changes not by a lot after that point. So the general shapes of your titration curves are going to be important, right? So we're going to be taking a look at differences in shapes of the titration curves. That's the first difference, and then we'll take a look at some of the differences in the calculation as well. So this specifically here is showing if we start off with 25 mils of a 1 molar HCl solution. So just as a quick reminder, okay, we have our flask. Let's say our HCl is in here. Okay, and then from our burette, like so. That's where the NaOH is. And as we add sodium hydroxide to this, right, that is essentially what we're doing. And we're charting the change in pH. We have a pH meter in there, for instance. We can see how that changes as a function of the volume of base sodium hydroxide that we're adding. So let's take a look at calculations that we can do to help us study this in a little bit more detail. All right, so let's take a look maybe initially at a starting point in this. And we can calculate the pH, by the way, at every single point in this process. So let's take a look at the calculating the pH at after 10 mils. So 10.0 mils of the 0.100 molar NaOH solution has been added to 25 mils of same concentration, 0.100 molar HCl solution. Right? So here, we look at the total volume at that point, it is 35 milliliters. Okay, and remember now your concentrations are given in this case in molar or molarity. Okay, and we want to make sure that all our units are in the same units. For example, molarity is moles per liter, but we have our volumes in milliliters. So we would either need to convert the volumes to liters, or we can convert the molar to millimolar. Okay, and this is the same, and we'll make our calculation a little bit easier here. So I'll put this on the right side. So we'll say recall, or you can actually derive this. 0.100 molar is the same as 0.100 millimoles of NaOH, or whatever the thing is, divided by for every milliliter of that. Okay, so let me just recap what this means. So 0.100 molar means 0.100 moles per liter, right? Which is the same as 0.100 moles per 1,000 milliliters, right? So if I divide the top by 1,000, that gives me then 0.100 milli means 1/1000 millimoles. If I divide the top by 1,000, I divide the bottom by 1,000 as well. 1,000 divided by 1,000 is 1 milliliter, right? Which is the same as this. So it makes the calculation a little bit easier. So 0.100 molar is the same as 0.100 millimolar, or 0.100 millimoles per mil. Okay, and we're going to use that. If you want to work the other way, that's fine as well. It doesn't, you're going to end up with the same answer. So we can now calculate the number of millimoles of, let's see, what do we have? That we have. So we have 10 mils, 10.0 mils of the NaOH. So 10.0 mils times the concentration, which is 1.100 millimoles of the NaOH per mil. Okay, so that's going to give 10 times 0.1 would give 1.00 millimoles of the NaOH initially. The number of millimoles of the HCl. Okay, so what do we have? 25 milliliters. And the concentration again is 0.100 millimoles per 1 mil. Okay, so 25 times 1 would be 2.50 millimoles of HCl initially. All right, so the amount of HCl left, because remember now, the H plus and the OH minus react to produce H2O. So I have initially 1.0 of this. I have 2.5. I'm sorry, these are swapped. I have 2.5 millimoles of the H plus. I have 0.1. Let me see if I can get that right. I have 1 millimoles of the OH minus. So when this reacts, right, obviously here I'm going to have some of the H plus left over. Okay, so I'm going to use up all of this. I end up with 0. I'm going to subtract that. I end up with 1.50 millimoles of the H plus. All right, and this is what I have after these two have reacted together in that total volume of 35 mils. So the concentration then of the H plus after adding those two together would be the 1.50 millimoles left over divided by the total volume, which now is 35 milliliters. Okay, so that is going to give 0.0429 molar, and then I can take my pH, negative log of that would give 1.37. Okay, so the pH after adding 10 milliliters of the sodium hydroxide is actually 1.364, 1.37 rounded to 2 decimal places. And we can go through and do that with all of these different time points, all of the different volume points along the addition over here, right? So the thing to keep in mind, right, with this strong acid, strong base is that these two things will react in a 1-to-1 ratio completely with each other. And we can determine how much of whichever of these two things is left over. How much is left over? How many moles is left over? We're going to divide that by whatever the total volume is. And that's going to give us either the H plus concentration or the OH minus concentration, when we can then determine either the pH or the pOH of that solution. Okay, so the calculations for the strong acid, strong base tends to be a little bit more straightforward than the ones we'll see afterwards.